All right, so it's time to start. So the next talk in the session about tooling is from Kristoffer, and he will talk about interpreting Julia code. So go ahead.
Thank you, Fredrik. So yeah, my talk is called Interpreting Julia Code, but first we need to talk about what is interpretation and how it differs to compilation. And it's a little bit hard to give like really solid definitions, but it's kind of a little bit hand-wavy, but with compilation you often do like a full program analysis and then you produce some kind of artifact that you then directly execute like a program. With compilation you often do some kind of full-scale optimization on the whole thing in one step and then you run the code. And you often catch some type of errors before you actually run your code. With interpretation, you kind of do things as they come, where you do execute code statement by statement without doing much analysis up front. Most decision making is done during the runtime, and you don't cache so much of the processed code. You can cache some kind of like bytecode from it. There's typically not many optimizations, and you often have some kind of a virtual machine running that does dispatching to instructions and store things like function argument variables and so on. So what's Julia then? Is it compiled or interpreted? I would say Julia is definitely compiled. There's no like virtual machine running. It compiles to machine native code, but it's done in a little bit special way where code is compiled incrementally and more on demand, but it's still compiled. Errors, though, are usually delayed to runtime. So if a type error is thrown in the forest and no one is there to hear it, does it actually cause any harm? With Julia, we say no. But there's also work in more traditional upfront compilation with Julia. So we have this --trim, and there's a talk later about that here. So why would we want to interpret code? Well, we can just ask ChatGPT, right? So let's see what it says here. It says that you can have rapid feedback and iteration, and you can see the result immediately in the REPL. But I mean, we have a REPL, right? Dynamic features, reflection, runtime code generation, evaluating user-provided scripts on the fly. I mean, we have reflection, we have revise, we can do this even though we're compiled. Simpler tool chain, no separate build link step. You just install the interpreter and run it. Well, we just install Julia and run it. It's pretty easy there too. Graceful error handling, errors surface exactly where they occur, and if you know in Julia the stack traces, they also surface exactly where they occur. So it seems that there's no reason to interpret Julia code here according to the all-knowing ChatGPT. But in Julia there's actually a few reasons. One is to lower latency. Running the full Julia compilation pipeline can take a bit of time, while with interpretation you just start executing straight away. And if you're running scripts or just top-level code where it doesn't do that much work compared to the time it would take to compile it, it might make sense to interpret instead. Sometimes with Julia, you might not have a compiler available in some certain scenarios, then you can fall back to interpretation. And you might also have better debug information. With native Julia code, it's hard to sort of execute it interactively, step by step, and see what's going on. It just kind of goes by its own and executes for you. So if you're doing it in an interpreted way, you have more control over the execution. You can track things like the exact state of the program, the local variables, and so on. So first I want to talk a little bit just for some background about the Julia compilation pipeline. And Julia, I would say, have almost a unique set of tools to follow through the exact compilation pipeline. So we can start here. The first step is that we parse the code. Code comes in as text, but it's kind of hard to programmatically work with text. So parsing turns this text into a more structured form in the expert data structure in Julia. And Julia now uses JuliaSyntax.jl for this. It used to do a scheme version, which is still used for bootstrapping, but after that's done, then it's the Julia one that takes over. And macros work on this level, so it takes an AST, which is what you get after parsing, and returns another AST. And after you're done with parsing, you move on to lowering. And lowering kind of simplifies the richness of the whole surface language or the whole AST into kind of a smaller set of building blocks. And all future analysis can then work with this simpler structure. And this does not depend on input types to a method, for example. So if you lower a method, it doesn't matter what the input types are. The lowering doesn't know really what's type and so on. It's kind of a syntactical process. So some things that lowering do is macro expansion. So if you have a show macro, it expands that to what the macro says it does. You do scope resolution. So if you have variables x that are in different locations in your functions, it might not refer to the same variable. So which x's are actually the same variable. It does control flow linearization. So if you have if-else stuff, it changes that to just go-to branches. It does the iteration protocol lowering. So if you have a loop, like a for loop, it changes that into iterate calls. It does some other things, function calls. If you have string interpolation, it changes that to string function calls. So if we go back here, we used to have this mySum was the text there, and then after lowering, we have something that is more, it looks more complicated, but it's more simpler in a structural way. So we have the iterate calls there, for example, and so on. The lowering is right now written in Scheme, but if you've been here earlier today, there's a lot of talk about this Julia lowering, which is a Julia version about for the lowering, and that's in progress. I put 1.13 question mark, maybe. We'll see. Then after lowering, we move on to type inference, and what that does is it assigns a type to every statement. So we have exactly what we have on the previous slide, except now after every statement here, you can see there's a type. And this is sort of the driver for almost all future optimizations. If you don't have types, there's not that much you can do. Not all statements, though, might resolve to a concrete type if you have like type instabilities, or if you write the code in a sufficiently complicated way, there might be some approximations done by type inference, but that's the step to get types on everything. Then we run the Julia optimizations. Now when we have types, we can sort of resolve what actual methods we are dispatching to. We can do something called scalar replacement of aggregates, which is if you have, for example, tuples, which is a sort of a collection of things, so we can split that out into its components. Constant folding, if things are constant, we can just compute them before we even run it. Dead code elimination, and the slot to SSA conversion, which is if we look before, we have these local variables, s and x and so on, while now after they are not even represented there, they've been turned into an even more simpler form. And we don't have really any function call here except to the most basic built-in function calls. And then we turn this into LLVM IR and run the LLVM optimizer on that. And there's both Julia-specific LLVM optimizations, but then also the general LLVM optimizations. And at this point, if we look at LLVM, we basically, there's no traces that this originally was Julia code. It's sort of gone down to this code could have come from any language. And then finally, LLVM selects actual instructions that will run on the CPU based on the current CPU target. And in this case, what we ended up with is these SIMD instructions for doing multiple additions in one CPU instructions. So we started with just a loop with plus, and in the end we ended with, this is for one iteration loop. It has done some iteration unrolling, so it does 4 of these for every loop iteration. And if you want to write an interpreter, then I would say the lowered code is a pretty good abstraction level, because if you haven't run lowering, there's a lot of things you have to do, like the scope resolution. You have to do the loop to the iteration protocol, and after lowering, you have a more simpler thing to look at. You could also say maybe I want to run type inference on that as well, but that adds some latency, and if you don't add much any more further optimizations, there's not much point of having types everywhere. You could use it to divertualize some calls, but I don't think that would give you very much. And if you go even further with optimization, you lose quite a bit of debug information that for the things we're going to use it for here is pretty important. So if you want to write the Julia interpreter, what is it that you need? Well, first you kind of need to manage the state, which is these say SSA values. If I go back, every line here is an SSA value. It just makes it easier that every single statement has one value. You need to have check on the local variables, where you are in the program, the call stack, the static parameters, and so on. So you need to manage the state, but also you need to do the execution, which is like, okay, now I'm going to run this statement. It has something. I'm going to do the control flow, the go-to stuff, and so on. And then this is not really needed to interpret, but having some debug functionality like breakpoints and inspect local variables and so on is nice. So there is an interpreter in Julia itself, which is written in C. and it's used in some cases. So for top-level code that is unlikely to benefit from compilation, like it doesn't have any loops, for example, then Julia will try to interpret it instead if there's no compiler available, or if you have disabled the compiler with this -- compile flag, it will interpret things. And there are some fallback cases where it will try to interpret things where something went wrong with the compilation. Yeah, as I said, it's written in C, but it's not really made with debugging as a goal. It's more like I would say a latency thing and also this fallback thing. And if we just look a little bit at the code, we have some state here, and just by looking at the names, we have the local variables are stored in some variable here, static parameters, like what module we're interpreting now, so we know if we're accessing a global. And this is a bit of a slide code, so I've removed some stuff and so on just to try and make the point, but we have some state here, and then we have our execution engine where we evaluate a statement, and then we're looking what type of statement it is. For example, is it a go-to node? Well, then we set the instruction pointer where we're going to execute next to where that go-to node tells us where to go. If it's a go-to if not node, we have to evaluate the condition, and depending on that, we might go to that one. If it's assignment here, we have to calculate the right-hand side and where to assign it and so on. So we basically have, for all types of statements we can have, we branch on that and we do what it means. So that was the C one. Then there's also JuliaInterpreter.jl, which is an interpreter for Julia code, but it's written in Julia. Just to give some history, it was originally called AST interpreter, started by Keno in 2016, and it was used in the very old debugger called Gallium. Then it was branched off as AST interpreter 2 to kind of still work with Julia even though Gallium was discontinued. And then Tim Holey took over in 2019 and further did a lot of development on this. It got renamed to Julia Interpreter. And then I, Sebastian, Shuhei, and other people have done some stuff on it as well. And it now powers a little bit of JET and the command line debugger, the VSCode debugger, and Revise. It's used for those. So if we look a little bit on the code in Julia Interpreter, and we also have some state and we have an execution engine. So the state we have is quite similar to the one in C, but there's a little bit more stuff in there. So we have some scope, which is what method we're evaluating, all the statements, and things like that. And then we have local values, static parameters, and so on. Everything we need to keep track of to interpret. And then it gets put into a frame. So that's sort of the state. And then we have the execution. So we're stepping an expression here. And we're checking what type, again, the statement we have. If it's a goto node, then we set the program counter to that, what that goto node says. If it's a goto if not, we do this. If it's an equal, we do this, and it continues. And then we just move on to the next statement here. So if we just compare a little bit the structure of the C interpreter versus Julia interpreter, you can see it's virtually the same. We have the checking for the goto node here in C. We do the same in Julia interpreter. We're checking for the goto if not. We do the same here. Assignment here, so they're kind of structured very similarly. Yeah. So there's good stuff, and there's bad stuff, and there's ugly stuff about Julia Interpreter, so let's start with the good stuff. So I would say that Julia Interpreter currently powers many useful tools, and that's sort of one of its strengths. It has enabled a lot of useful tools to be built on top of it. So the first one is Debugger.jl, which is the command line debugger. So we're keeping with the mysum function here. If you load the debugger, you can enter it, and it shows you the code here. You can add a breakpoint at length, for example, and then if you continue, you hit that breakpoint. You can show the backtrace, and you see all the local variables, and you can execute code in here, and so on. So it's a pretty good debugger, I would say, for if you have quite simple code. And that's sort of built on top of the Julia Interpreter then. And then there's also the VSCode debugger, which is works in a similar way, except that it's just a different graphical interface presented to the user. So you can also set breakpoints here, and you can see the local variables and do expressions that gets evaluated every time you step and so on. And Revise also uses Julia Interpreter. Most of you probably know what Revise does, but just as an example here, it can hot reload your code if you have it in scripts or packages. You just edit the code, and it's going to immediately notice that and update your code in your session. So here's one example. If I load revise and I use this include t, it's going to start tracking any changes to this file. And if I write it out now, it's just my sum function that I have here. But if I went into my editor and I added this thing without having to include anything else, if I just run the function again, it added this hello JuliaCon to it. And it's also used in very few, but some packages actually use JuliaInterpreter to speed up their tests. So in chainrules.jl, they're using JuliaInterpreter because they are so compilation time bound that just interpreting their whole test suite is faster than having to compile the whole thing. So what they did here was that instead of just including the test file, they just interpret it instead. So some more bad stuff about JuliaInterpreter. Well, one thing is that its speed is not very great. So if you remember, after we did all the optimization with the normal code, it turned into 16 additions per loop iteration, and that was 4 SIMD instructions doing 4 additions each. Now, if we look at one single iteration in a loop, JuliaInterpreter has to get through all of these functions and built-ins and so on. And every time, we don't know, like we have to resolve which are we going to dispatch to, and we have to look like, is it this type of statement for everyone and so on. So it has to chug through quite a lot just for a single loop in this, while when we did optimization, we did 16 loops with CPU instructions. And I mean, the way we write Julia code is that we know there's going to be an optimizer that runs things. So we don't worry about small functions. We don't worry about like tuples that they're going to get allocated because the optimization is going to take care of this and so on. So it's a Julia code is a little bit of a tough case for interpreter because so much of it is written with the knowledge that there's an optimizing compiler there. There's some stuff you can do to try to speed things up, and that's by not recursing your interpretation down in sort of uninteresting modules or methods. So if you don't care about, I don't care about any debug stuff in base, so I'm just not going to recurse down with the interpreter there. I'm just going to run that compiled. But sometimes, if you write some certain syntax, if you do that, you'll miss some things. So for example, if I write a comprehension like this with G gets in this comprehension, if we actually look what's going to get executed, we're going to create a generator with some anonymous function here, and we're going to collect that. So if I just ignore base, I'm going to miss the calls to G here. So if I would want to be interesting, if I maybe had a breakpoint on G, if I just did this, I'm going to not hit that breakpoint because when it runs, it's actually going to run in compiled mode. And Julia is often used for computationally heavy workloads, as you know, so your own code might be the thing that takes time. But for me personally, quite often, just making the input a bit smaller works quite well. And instead of running your full finite element code on it, you just run it on like a little smaller mesh, for example. Another thing that's a bit bad is it can't really follow into the runtime and scheduler. So if I have two similar functions here that just does something in a loop, one does it normally and one does it in a thread, and then I set a breakpoint on G here. If I just interpret this normal F, then I'm going to hit the breakpoint, then JuliaInterpreter is going to stop and tell me, okay, you hit the breakpoint here. But if I run this threaded, it just goes through it and it misses the call to G here because this actually gets passed into the scheduler and that's written in C and so on, so we can't really follow the execution through all the way there. It's also quite heavily tied to Julia internals. So many times when people change the Julia internals, they also fix up the interpreter in C, but maybe they forget about updating Julia interpreter, and it's always lagging a little bit behind the state of things on the master branch. Revise uses Julia interpreter, and that's actually tested as part of CI, but just because the Revise test pass, it doesn't mean that Julia interpreter is actually fully functional. And sometimes core contributors can be a little bit like, oh, I made this nice internal change, but now I have to update this Julia interpreter code that's all messy and not how I would have written it. So it can be a bit of a friction there. Some of the more ugly stuff, I just had to put some stuff in here so I could get all three parts into it. But so one thing is this wrapper step through. So sometimes Julia creates this internal wrapper functions. And you'll see that is, so if you have default arguments or keyword arguments, so if we look here, I'm creating one function, takes x and then y, which has a default argument now, and also a keyword argument, and it just adds them. Now, if I enter this with the REPL, you immediately goes to this x plus y plus z, which is what you expect. But if I actually look at things, if I look at what the lowered code of f(1) is, it just calls another function with this 1, which was the default value of y, put in there. Okay, but then I look at that one. Oh, but then that calls something a little bit strange here, because now it has put in the keyword as well. Okay, so now I look at the keyword, and then it does a bunch of sorting, and it defines this other weird function, and so on. So finally, I'm here with this var, some strange things, which has a bunch of stuff in there, and that's where the actual body of the code is. So Julia Interpreter and the debugger sort of have to realize, like, all this stuff, it's not really interesting for a user, and step through that. And doing this pattern matches, that changes with the Julia internals, can be a bit messy. Another thing is C-call and C functions. Those require a compiler to run. If you look at the C version of the interpreter, it actually, if it hits one of these C calls or C function, it's just going to error. Because you actually need a compiler to be able to do this properly. And in Julia Interpreter, we actually look through the code and see if there's going to be a call to a C call or a C function. And then we kind of move that call into a separate function that we actually run in compiled mode. So we cannot fully interpret the whole language. We have to use the compiler for those parts. A little bit about the future. One possible thing is if we could merge ASD interpreter, the .c, the C version, and Julia Interpreter. I mean, it would be nice to only have one implementation, but they also serve quite different goals. The C one is mostly for latency and things like that, while the Julia Interpreter also tries to provide quite a lot of debug information, and it's possible there's a little bit of conflict there. Maybe having all this debug information makes it slower. So, yeah, I'm not sure. When it comes to the speed, maybe we can have some more friendly bytecode, friendlier code to interpret. There's some ideas in a pull request here from 2019 by Tim Holy. It hasn't gotten a lot of attention since then, but with Julia lowering.jl coming, I would say that probably brings a lot of new ideas and freshness and willingness to work on this. So it will be quite exciting to do this. I mean, maybe someone creates a whole new interpreter from scratch based on Julia lowering, or maybe Julia Interpreter gets updated. So yeah, I think when this Julia lowering is in place, quite a lot of interesting things can happen when it comes to Julia Interpreter. Yeah, that was it for me. Thank you.
Can you go to the slide with the generator example?
Yes. Was it here? Yeah.
Yeah. Okay, so I think I suggested this once before, but I don't think anyone understood me. It seems to me the way to fix this is that when you, instead of passing G into the generator constructor,
you're not actually passing G here. You're making a new closure that passes in the X here into X2. But
it's the closure that calls G. But yeah. But there's some function there. Yeah. There's a closure. So instead of passing the closure into there, the way to fix this would be to wrap that in a new thing that calls the interpreter on the closure.
Yeah.
Right? Because then you have compiled code which calls a function which re-invokes the interpreter.
Yeah. You would sort of lose the way you got there, I guess, all the steps on the way until you start up the interpreter
right,
afresh.
You'd have to have like a stack trace that you.
Yeah, but maybe you don't care so much about exactly how you're going through base to finally end up at your function. Yeah. So and then
couldn't you also, like anytime there's a breakpoint in a function, replace that function with a version of that function that is the interpreter interpreting that function?
Yeah, so I think there's been some attempts at doing that on like a bigger scale using, I think it was cassette maybe, or at least something that like it just uses the invalidation thing to you change one function to have a breakpoint, and that sort of invalidates code, and then when the compiled code calls that function, it calls the new one. It might work. I'm just a little bit worried about latency in that you have to recompile code and so on that's going to call that one. But and it's the same there. You're losing the path you took to get there because you're starting up a new interpreter session there. But yeah, that's also an interesting thing to work on.
If I can also comment on that, I think when we were first working on Julia Interpreter, we actually also had two goals, really. One was to get a functional interpreter, but the second was a possible application, and you mentioned it in some packages, using it to speed up their tests, as an experiment in whether we could interpret more things in Julia and not hit the compiler so much. So we very deliberately were trying to not do anything that would generate extra compilation in how we went at it. I mean, I think we know much more now, and we have package image caching and all this kind of stuff. So I think we could revisit, in principle, those decisions. But you know, it would be there would need to be some fairly fundamental work done to implement.
For the generator case, I think you've got a closure there already. So why not pass the interpreter state through the closure? So you can just continue on in the interpreter.
Yeah, well, you still lose sort of all the intermediate steps in between, but then maybe you can sort of patch things up between the time when you call G and F. Because I mean, if there's many steps within base there that finally ends up calling G, you're not going to have all those steps. So I mean,
well, in this case here, this is a Julia generator, right? So you can actually generate whatever code you want, right, for that for loop. So you could track everything, I think.
Yeah, but at the same time, we kind of want to not do too much processing, I guess. We kind of want to be at the part where we're just blasting through the stuff here, basically. Because if we do too much, I mean, in the end, we just have a new version of Julia that has better debuggability. If you take it to the actual limit of improving things and making it faster and so on. So, at least to me, there's always this thing like how much work should be made at making like optimizations for this and so on, versus maybe another path is to make, when it comes to debuggability, is maybe try to make Julia itself more amenable to debugging. Like most languages don't need an interpreter to be debugged. They just work with a debugger. So that would be, I would think, quite a lot of work. But maybe that would be, if we're on a local optimum now, maybe that would be more of a global optima where Julia itself is better at getting debugged. But it's hard because Julia is JIT compiled and it does many things in a kind of a non-standard way compared to how debugger are used to see code getting executed.
All right, one more quick question. If not, then we thank Kristoffer again.
Thanks.